Hi, Year 11s. I'm going to work through the entire mock bit by bit, and you can just fast forward to the questions you got wrong and hopefully understand a little bit better about maybe where you went wrong and how to improve. To start with, it's asking you in question 1 about what type of substance is hydrogen. Most of you got this right, so I'm not going to spend too long on it. But if it's an element on the periodic table, then it will be an element. Compound, of course, is when you've got two or more elements bonded together. A mixture is when you've got two or more substances not chemically bonded together. So key stage 3 stuff really, so that's an element. The second question is asking you to find out which is a mixture of compounds, and so you have to look on there to see which ones are compounds. So to be a compound, it has to be a mixture of, or a substance where you've got different elements combined together. So in picture A, you've got this molecule here, which has got two different elements. This one's got two different elements as well, though it's a bit harder to see. So this one must be the answer because it's a mixture of different compounds. This one is a mixture of elements because this is an element. Even though there's two of them joined together, it's the same thing twice. So that's an element and this is an element. This is an element and a mixture combined, and this is a pure compound. So it's that one was A. Question C is which one is a mixture of elements? Well, I've already covered that. Mixture of elements must be a B, and I say most of you got those questions right. So we'll move on. Over the page, we've got a couple of questions on distillation and filtration. So the first one is a bit of a key stage 3 question, really. Sand can be separated from a mixture of sand and water by filtration, or filtering. If you wrote filtering, we allow that. Filtration. Okay. Tiny bit harder now. You have to think a little bit here. You're given some information about fractional distillation. So if you're not sure about fractional distillation methods and what's going on there, fractional distillation is all about separating a mixture of liquids with different boiling points. That's what's going on here. And when you heat up the mixture of liquids, the one that's going to boil first is the one with the lowest boiling point. And that one was C. And again, loads of people got that one right, so well done on that. And what would happen, this one is the first one that most people got wrong actually. Okay, so when you heat the liquid here, the vapours travel up the fractionated column and travel through the condenser. Now this is a liquid. We don't know what liquid it is that's travelling through here. We're not told that. If it's 78 degrees, I'm guessing it's ethanol, which has a boiling point of 78 degrees. But it's asking you in the question about the water, what happens to the temperature of the water. Water goes in at one end of the condenser and out at the top end. The water, remember, is a jacket around the outside of the condenser, and that, as it goes from the bottom to the top, will be warming up because it's there to cool down the vapours of ethanol or the liquid C, whatever it is, as it's passing by. So the water, of course, is going to heat up. It's going to heat up. Temperature is going to increase. Okay, it's going to become warmer. And then, how would you obtain some sodium chloride crystals from sodium chloride solution? So you've got a solution. In other words, you've got sodium chloride dissolved in water, and you want to get pure sodium chloride. Okay, so if you just simply heated it up until all the water was gone, any impurities that might be there would stay there. This is about crystallizing them, not just heating all the water away because you end up with a kind of clumpy mess. You want to grow some crystals in order to get them nice and clean. And what you would do, typically the way to do this is to take a beaker of water, put an evaporating basin on top, heat the water until it boils, and the steam from the water will heat the evaporating basin that contains the solution of sodium chloride. And the first point there really is you heat the solution until some of the water is lost. And the point, how do you know how much water to lose? Well, it's when crystals start to form, and the way that you do that, you typically dip a glass rod into the solution, and if crystals form on the glass rod when you take it out of the liquid, then it's telling you that it's ready to crystallize. You've got rid of enough water. Typically reduce the volume by about half, or evaporate some of the water would have got the mark. Okay, so evaporate some but not all of the water for the first mark. So heat, to evaporate half the solution or some of the solution, would have got the mark absolutely fine, or ideally remove it until the point at which it starts to crystallise on a glass rod. The second mark was you then allow it to cool down. If it cools down, the crystals will grow nice and slowly in the solution. You can then filter those out and they'll be lovely and clean, pure crystals. That's crystallization, the 2 marks there. We'll do question 2 as well. This one was done, this was a mixed bag, this one. So this is not an easy dot and cross diagram to draw. There's a method here that you need to use to draw covalent diagrams. We know it's covalent, partly because it's told us, but also because it's 2 non-metals that are bound together. So therefore it must have been a covalent bond, which is a sharing of a pair of electrons. It's the definition you need to learn of covalent bonding, isn't it? So the first thing to do is to find out, or to look up, or to know how many bonds each type of atom makes. And nitrogen is in group 5, so each nitrogen must have 5 electrons in its outer shell, because it's in group 5. You can see that from the periodic table. Because when atoms bind, they end up with full outer shells. I'll draw a nitrogen atom here with 5 electrons in its outer shell. It binds in order to make a full outer shell. You result always in a full outer shell, which means it can make a total of 3 bonds with another atom. In other words, it has what we call a valency of 3. So it makes 3 covalent bonds. Nitrogen always makes 3 bonds. So the first thing to do is to draw the 2 nitrogens, and in each case, each one must be making 3 bonds, and the only way that can be done is by drawing it like so. So you draw the line diagram first, showing the right number of bonds between each atom, and then remember that each line there represents a pair of electrons. So we must have in here 6 electrons. We usually represent electrons from one atom as dots and the other as crosses. Now that's part of it. That would get us one of the marks, 6 electrons in there. And then we always end up with full outer shells. So this shell's now got 6, so there must be 2 more in there to make it 8. And this one also has 6, so it needed 2 more to make it 8. And that's the answer. Also remember that nitrogen started with 5 electrons, 1, 2, 3, 4, 5, or in this one 1, 2, 3, 4, 5, and it picks up 3 more from the other nitrogen to make that right. Nitrogen, like the vast majority of simple covalent substances, is a gas at room temperature. This is a common question, a very, very common question. And it isn't always answered very well. You need to answer this well to get the marks. So the first thing you need to know is that when you boil simple covalent substances, you do not break the bond. The bonds are extremely strong. What you're breaking is weak interactions between molecules. Each N2 is a molecule, and there's these weak interactions between the molecules that we call intermolecular forces. So you get a mark for mentioning intermolecular forces. And if you mention bonds or breaking bonds at all, you lose marks. Okay, so you've got to be really careful about that. You have to mention that those intermolecular forces are weak. So get a mark for that, and a mark for saying intermolecular forces, or forces between molecules. You can't talk about bonds. And then the third mark, which is, even if you get this bit right, the third mark's quite tricky to get. You have to say that those weak intermolecular forces are easy to overcome. In other words, you don't need much energy to overcome them. Easy to overcome, or ideally little energy to overcome. That's the perfect way of answering it. Okay? You do need to know, just factually, you just need to know a number of structures really well and be able to talk about them in detail. So you need to be able to talk about in your exam graphite and diamond and graphene and Buckminster fullerenes, all of which are allotropes, versions of, if you like, or different structural forms of carbon. They're allotropes of each other. They've got quite different structures, and therefore they've got quite different properties. And by properties, I mean things like melting points, boiling points, conductivity, all that kind of stuff. You're asked in this question to talk about graphite. And the mark scheme here I thought was quite generous, but we'll work our way through it. So the thing about graphite is you're expected to know, although this question does tell you, that it's soft and a good electrical conductor. So we've got to explain both of those things. We'll do one at a time. So to describe the structure of graphite, you must be talking about, and I'm not going to draw a picture here, but you should certainly be familiar with the picture of graphite being in layers. And you'd get 1 mark for just making it really clear you know that it's in a layered structure. And I like to think of those layers as a bit like a pack of cards. So each layer of graphite is like a card, and those layers are attached to one another, but they're attached to each other with quite weak forces. And so the layers can slide over each other. And that's the reason that graphite is fairly soft. And it's that reason that graphite is used as a lubricant as well. So it's quite soft and a good lubricant because the layers can slide over each other. So that might be how your exams next year go. You also have to explain the good conductor of electricity. And you might simply remember that it's got delocalized electrons, and that would get you 1 mark if you mentioned that it's got delocalized electrons. But really you need to be able to explain why it has delocalized electrons. And if you were to look at a layer of graphite, I'm going to draw a picture of one from the top. What it looks like is a series of hexagons where each carbon is bonded to 3 others. I'm not very good at drawing, so this is my best effort. There we go. Each carbon is bonded to 3 other carbons, and if you remember that carbon's in group 4, and 3 of carbon's electrons are involved in making covalent bonds with other carbons, and so there's 1 spare electron per carbon. 1 spare electron per carbon. So you get a mark simply for saying each carbon is making 3 covalent bonds, or is bonded to 3 other carbons, I prefer. But I also like you to say, really, because sometimes exam papers will have this, you have to say that each carbon atom has 1 spare electron, and that electron is not fixed in place, i.e. is not localized, it is delocalized. And those electrons flow between the layers, and that's why they can carry the charge. So that's that one. Last one before I take a break or break the video up at least, is a picture about Buckminster fullerene. Many of you have forgotten the structure of Buckminster fullerene, but it was given to you, so that was quite handy. And it has a structure which is 60 carbons joined together in a bit like a football in a ball. Okay, and you don't need to know loads and loads about Buckminster fullerene, just a few details, like the fact that it's a good lubricant, and that's what this question is about. It's a lubricant simply because it's got a spherical shape, a ball shape would have got you the mark, and those spherical ball-shaped molecules, because they are molecules, can simply roll, not slide, but roll over each other. Look at the carbons closely, you'll notice again that each carbon is making 3 bonds. And so for the same reason as I just explained with graphite, they do conduct electricity round the surface of the ball. If you had a second molecule of C60 over here somewhere, electrons can't jump from here to here. So in bulk, if you had lots of them together, they don't conduct electricity across a long region of space or something. But across the surface they are actually conductive, a bit like graphite and graphene. Okay, but this is about lubrication, so good lubricant because they're spherical and roll over each other. I think I'll stop there and I'll do another one in a sec.